Hey guys, Miss Marusik here, and in this video we're going to talk about the ideal gas law. This is just another equation that we can plug our variables into to solve for an unknown variable, very similar to what we've been doing on all of these other gas laws. So for just a moment, before we look at the notes, I actually want to look at our formula chart for just a moment at that behavior of gases section. Hopefully we'll notice a few familiar things in here, such as P total equals P1 plus P2 plus P3. Hopefully we recognize that as being Dalton's law. You'll notice down here we have P1 V1 over N1 T1 equals P2 V2 over N2 T2. Hopefully we recognize that as being the combined gas law. Remember Boyle's, Charles, Gay-Lussac's, Avogadro's, their formulas are all hiding in that combined gas law. But that leaves us with three other equations here. All of these equations work together for the ideal gas law, although the main formula for ideal gas law is this first guy right here, PV equals nRT. So that's where we're going to start our discussion here. Hopefully we recognize some of the variables in here. P is of course for pressure, V is for volume, N is for number of moles, T is for temperature. It's the same variables we've been dealing with, but we'll notice a new one here, and that is R. R is representative of the universal gas constant. Now, being a constant, it is actually given to us on our constant and conversion section on our formula chart. So if you look about halfway down, right underneath the pressure equalities, you will see R here with three different possibilities to use for R. And we're going to talk about those here in just a moment. I do want to give a word of warning. I see people accidentally use the pressure equalities sometimes for R instead of using these actual values of R. So be very careful. We only use these pressure equalities when we're trying to convert back and forth between pressure units. If you're doing the PIVNERT or PV equals nRT equation, you want to make sure you are utilizing these R values. Now, I mentioned PIVNERT just a second ago. That's kind of the nickname for this formula, and you can see why. If I said the letters kind of all in a row, it looks like I would be saying PIVNERT. So on that R in PIVNERT, we had three options here. The three options look very similar, but with one key difference besides the number. If you look at the units, you will notice that they all have liters, moles, and Kelvin in them, but they each have a different pressure unit. So this 0.0821 value has atmospheres in it. 62.4 has torrs in it. 8.314 has kilopascals in it. So depending on the problem that we're doing will depend on what our pressure unit is, and so we want to pick an R value that matches with our pressure unit. So let's say I am doing a problem where I'm utilizing atmospheres for my pressure unit, then I would want to pick the R value that has atmospheres in it. That'll keep me from having to convert pressure units. Now, I do want to mention really quick, you'll notice that there is not an R value for PSI. That is mainly because we don't use PSI that much in science, even though it is common to see, like when you're measuring your tire pressure here in the United States. Pounds is, of course, an American system unit. So even like overseas and stuff, they tend to use kilopascals for their tire pressure. But the other one that's not on here is millimeters of mercury. But I have kind of a hint or trick for y'all. And that is if you remember, 760 millimeters of mercury is equal to 760 torr. And what that means is that those two scales are actually the same. And so even though this one says for torr, you could also use 62.4 for millimeters of mercury. Now, there's one other thing that we have to be cautious of when we're using the PIVNERT equation. Once I've picked an R, I want to make sure that everything is matching up with that R unit, okay? Now, obviously, the pressure would match up if I picked it correctly, but I also want to make sure that my temperature is in Kelvin, which we already know that should be in Kelvin, that my amount is in moles, But I also want to make sure that my volume is in liters. If it's not in liters, it won't match up with the R value, and your answer is going to come out incorrect. And so it's going to be a hot mess. So this is the one time where it really does make a difference what unit we're using for volume. Now, the other big question I get a lot of times is, how do I know that I'm going to be using this equation and not, say, the combined gas law? Because this has a lot of the same variables that we saw in the combined one. The key difference here is that I am only going to have one set of conditions, one volume, one pressure, one temperature. Those things aren't changing. I'm just trying to find one of those variables that's unknown. With the combined gas law, you're going to have two of everything because you're trying to convert to the new conditions. But here, I'm just trying to find one of the conditions that's unknown. I'm not changing to a new set. So that's the big difference here. Now, I mentioned just a few moments ago that there are two other equations on the formula chart. So I want to talk about those as well as talk about what you see on here for a moment. First off, if you'll notice on the side over here, we have N equals little m, which is mass, over mm, which is molar mass. And that N is in common with pivnert. So what you are allowed to do is to take this and substitute in for N within pivnert, and that will get you to this equation here, that PV equals mass over molar mass, again, making in that substitution for N, times RT. So again, the N is replaced here with mass over molar mass. Also, when you make in that substitution, you will notice that mass and volume are both in here. And I know that if I'm doing, say, a density problem, that density is mass divided by volume. So if I did some rearrangement here of this, where I had mass over volume, in that equation, what I could do is substitute in the variable of D for density in for mass divided by volume. And that is what you'll see here. Here we have density in instead of mass and volume. And in order to do that, they've rearranged some of the other variables that we have present here. Now, this equation we do have on our formula chart. So molar mass equals dRT over P, which kind of looks like dirt over P. It looks weird, doesn't it, right? Okay. Now, one kind of quirk I do want to mention about density here is that in order to match up with all of the other units that we're using in various pieces, that instead of this being grams per milliliter like we're used to seeing, this is actually going to be in grams per liter. Liter is a much more applicable unit to use with gases because gases tend to take up a lot of space. If you kept it in milliliters, you'd end up with these huge numbers for your volumes. And so keep in mind that this density here is going to be grams per liter. And the reason why is because with those R, remember we had liters in those units. All right, with all that said, let's go ahead and look at a problem and also kind of take the time to see how these are a little bit different than what we did with the combined formulas. All right, so to start us off here, what I'm going to do is I'm going to go ahead and write all of my data out just like we've been doing on our other problems. So this is asking us to find how many moles of oxygen. So I am here looking for N. Must be put in a 500 milliliter flask, so that would be a volume. At 20 degrees Celsius, so that would be a temperature. To have a pressure in the flask of 1.77 atmospheres. All right, now I want to point something out about the data so far. Notice that I only have one set of each of these conditions, one pressure, one temperature, one volume, one mole value. I do not have two sets of conditions here. And that's the big difference between a combined problem where I do have two sets of everything versus an ideal gas law problem where I only have one set of everything. So that is the way to pick out an ideal gas law from a combined one, is that with ideal, you're only going to have one set of your conditions. So with that said, I'm going to go ahead and write that we're going to use the PV equals nRT, the ideal gas law equation here. And I'm going to go double check and make sure that I have not only my units correct, but also all of the variables that I need. So I'm actually going to talk about variables first, because you're going to see that once I make sure my variables are good to go, then it makes checking the units a little bit easier. So I notice here that I'm looking for moles, so that's going to be my unknown piece. I have a pressure, I have a volume, I have a temperature. So what variable do we not have yet? And hopefully we figured out that I need to pick an R value. Now, when I'm picking an R value, I want to make sure that I'm picking one that matches with my pressure unit. So notice here that our pressure is in atmospheres. So when I go to my formula chart here, and I look through these R potential possibilities, I want to pick the one that has atmospheres in the unit. And that's going to be this guy right here, this 0.0821. So what I'm going to do is I'm going to go ahead and write that here, 0.0821, and I'm also going to go ahead and include the unit, liters times atmospheres over moles times Kelvin. Now, what I want to make sure happens is that all of those units match up, so that eventually my units will cancel out. If I don't make sure they match up, then not everything is going to cancel properly, and the answer that I get will be incorrect. So looking through, we made sure that pressure matched up. That was the whole point of picking the R value. I noticed though that here the volume is in liters. So remember, in order for this to match up, I'm going to have to convert that milliliters into liters. Now remember, milli is 1 times 10 to the negative third. So you're going to have to move your decimal 3 places. And that's going to give us 0.5 liters. Now, moles do match up unit-wise, so that's good. And then, of course, just like we've seen on all of our other problems, this temperature is going to need to be converted into Kelvin. So 20 plus 273 would be 293 K. All right, so now that I have all of this in the correct unit, now I can go ahead and plug all of this in. So my pressure was 1.77. My volume was 0.5. My N is what I'm looking for. My R was 0.0821. And my temperature, once I converted it, was 293. Now, again, what we're trying to do here is solve for N. Since this is multiplied here, I can divide these over. So what I would do, let me scooch this up here just a little bit, is I would go ahead and multiply the 1.77 and the 0.5. And then I would divide over these other two variables here. So I'm going to divide over 0.0821, and I'm going to divide over the 293 in order to get that N by itself. And that gets me this variable right here, 0.03679002. I'm going to round for sig figs. I noticed all my original numbers had 3 sig figs, so 3 sig figs seems like it would be appropriate here. We were solving N, so this is going to be 0.0368, and we were trying to solve here the moles. Now, if we did this right, the units in this problem should have canceled out. Remember that 1.77 was atmospheres, 0.5 was in liters. This crazy guy right here was liters times atmospheres over moles times Kelvin. This guy was in Kelvin. So look what happened. Atmospheres canceled out, top and top on the opposite sides. Liters canceled out, top and top on the opposite sides. Kelvin canceled out top and bottom on the same side. And what that would have meant is to have moles on the bottom here, this end would have had moles in the numerator on top. And so that works out with all of those units that we were hoping to. As far as our law name, we would call this the ideal gas law. All right, let's go ahead and do a few more. So go ahead and flip the page for me. All right, so looking at the top here. Again, I'm going to start by writing down all of my data, kind of figure out what I've got happening here. It says I have 1.17 grams of helium. So I'm going to do mass equals 1.17 grams. Put into a 500 milliliter container. So I have a volume of 500 milliliters at 10 degrees Celsius. So T equals 10 degrees Celsius. What would be the pressure of this container in torr? All right, so kind of looking here. Again, I notice I have one set of conditions. One volume, one temperature, one mass, one pressure. So I know I'm going to be using some variant of Pivnert. Now, I do have kind of something quirky here. I notice that this has mass here, yet this has moles. So that doesn't really match up. However, remember, I have a substitution I could make in for Pivnert. As a reminder, our N, our number of moles, could be substituted in with mass over molar mass. Now, do you have to use this substitution? No. What you could do is convert the mass into moles using stoichiometry and just plug into Pivnert as is. That is totally an option. However, I usually like to use this substituted version because that kind of eliminates some extra work I might have to do. I only have to plug into my calculator once that way. So what I'm going to do is I'm going to rewrite this as PV equals mass over molar mass RT. All right, so now I need to kind of check my units and make sure I have all of the variables that I need. So I'm looking for pressure, so I know that's going to be unknown. I have my volume, I have my temperature right now. So let's think about what we're missing. Now, I kind of put the question mark here. Really, I should have put it over here. I have my mass, but I don't have yet a molar mass. I also don't yet have an R value. So we're going to have to pick an R to use. Okay, so quite a bit here that I'm missing. As far as the molar mass is concerned, think about what gas we have in this problem. If you look back here, it says that we have helium. And if I go look at my periodic table, I notice that helium is 4 grams per mole. So I'm going to use that for my molar mass. So again, this is specific for helium. If you had a different gas other than helium, then you would have to use the molar mass of that specific gas. On picking my R value, I notice here that we want the pressure in torr. So when I go over here and I look at my R values, I look through and I notice that the one that has torrs in it is 62.4. That has a unit of liters times torr over moles times Kelvin. Now, I'm going to use that to make sure everything else matches, okay? So torr obviously matches up. Does liter match up? Oh, wait a minute. This is in milliliters. So yet again, we're going to have to convert 500 milliliters into 0.5 liters. All right. Now, moles is kind of interesting here. The moles actually matches up with moles in molar mass. The grams here would match up with the mass. So all the units will still work out, cancel out, all that goodness. It just does so in a little bit of a different way. Kelvin needs to match up with my temperature. So 10 plus 273 would mean I need 283 Kelvin there when I plug in. All right, so now that I have all the pieces here, I can do my plug and chug. So my pressure is what I'm looking for. My volume was 0.5. My mass over molar mass would have been 1.17 over my molar mass of 4. My R was 62.4, and my temperature was 283. All right, now I can see that I'm trying to solve pressure. To get pressure all by its lonesome, these two were multiplied, so I would want to divide that over. So what I would do here is start by plugging in everything on this side of the equation. So I have 1.17 divided by 4. I'm going to close that. Then I had 62.4. I had 283. And then I'm going to divide over that 0.5. And I see that that gets this really big number here. Now, thinking about sig figs for a moment, again, if I look back at the original problem, everything had either 3 or 4 sig figs. So I'm going to use 3 sig figs. That would cut off this number right here. But don't forget, I need to still show that this was 10,000. So I would leave it as 103 and then use zeros as placeholders. And again, here we were trying to solve torr. So a really incredibly high pressure here. You could have changed this into scientific notation if you had preferred. So you could write something like 1.03 times 10. Let's see, 1, 2, 3, 4. So 10 to the 4th would have also been appropriate to show for an answer. Law name would have been ideal. All right, so here's what I want y'all to do. There's another problem down here. It asks, what is the molar mass of a diatomic gas if 1.60 grams of it are in a 500 milliliter container and they're exerting a pressure of 2,500 millimeters of mercury at 350 Kelvin? I want you to take a moment and see if you can solve that molar mass. Now, I will warn you, I know we can see that we would need Pivnert. Since it's asking for molar mass, it would probably be really good to use that substitution in Pivnert that has molar mass in it. But also I want to point out that our pressure here is in millimeters of mercury. So when you're picking your R value, remember there's not one that has millimeters of mercury in the unit, but remember millimeters of mercury is the same thing as torr. Those scales are the same. All right, so go ahead. Take a moment, pause this video, and see if you can try out the problem. All right. You think you got it? You think you were able to solve it? Let's check and see how we did here. All right. So first, in dark blue, I went ahead and wrote all of my data down. I'm looking for molar mass. As a reminder, that's grams per mole. My mass was 1.60 grams. My volume was 500 milliliters, pressure 2,500 millimeters mercury, temperature 350 Kelvin. I did need to pick an R value. As a reminder, torr is the same thing as millimeters of mercury, so I picked that 62.4 to make that match up. Now, you'll notice that the temperature was already in a good unit here. That doesn't happen all that often, but that was convenient. But I did have to convert the volume to liters. So again, we see that 0.5 liters being used there. And so then I just simply plugged in to my substituted Pivnert equation. So again, in for number of moles, I plugged in mass over molar mass. Now, I will warn you, the biggest issue I see people have on this problem is that your unknown variable is in the denominator. And one of your first things you want to do is get it out of the denominator if you're trying to solve the algebra. So what I would have done is, in order to undo this divided by molar mass, I would have multiplied by molar mass over here on the other side. Okay, so that would kind of bring it up to the numerator. So now, to get it by itself, I would simply just divide over 2,500 and then divide over the 0.5. That would have been how I would have solved the algebra. Now, I'll be honest, there's more than one way to solve the algebra. So solve it in whatever way makes sense to you. As long as you're getting a correct answer, doesn't really matter. Now, when you solve molar mass, you should have gotten 28.0 grams per mole. It asked a second piece to this question. It asked, what element does this gas represent? And it did tell you that this was a diatomic gas, which means when you got this molar mass, this was for 2 of that element together. So before I matched it up to the periodic table, I would have divided this by 2 in my head and then been like, well, that's about 14. And I would have then looked at the periodic table to see which element had a molar mass individually of 14. And of course, that's nitrogen. So this would have been diatomic nitrogen gas. Law name would have been ideal. All right, let's do another one on the next page. All right, so a little bit of a different problem here. They're asking us for kind of a different piece here. It asks what would be the density of oxygen gas at 70 degrees Celsius and 3 atmospheres. So I'm looking for density here. We're going to talk about the unit for density in just a moment. I know we mentioned it earlier, but we're going to talk about it again. The only other data they really give me here is temperature of 70 degrees Celsius and a pressure of 3 atmospheres. All right, so next, let's kind of think about what equation we might use to solve this. Well, obviously I have one set of conditions here, and so I'm thinking, well, Pivnert sounds like that would be a good option, but here's the problem. Pivnert itself does not have density in it. And I'm thinking, well, maybe there's like a different version or a substituted version I could use. And in fact, as a reminder, our alternate version is this guy right here. Molar mass equals dirt over P. So that D is our density. So instead of using Pivnert, I'm going to instead use molar mass equals dirt over P. All right, so let's make sure we got all the variables we need, yes? Okay, I know I'm trying to solve density, so that should be unknown. Okay, well, I have temperature, I have pressure. What am I missing? Well, I need to pick an R. And I also need molar mass. Now, let's think of what we need molar mass for. We need molar mass of oxygen gas, right? Well, don't forget, oxygen gas is diatomic. So when we do that molar mass, I know most of us remember oxygen is 16. I would need to times it by 2 and make that 32 grams per mole. Again, that is your molar mass of the O2. Okay, but I still need to pick an R, so let's talk about that. Let me bring up my R values here. Now again, I want to pick one that matches up with my pressure. My pressure was in atmospheres, and so if I look on here, the one that has atmospheres is that 0.0821. That is in liters times atmospheres over moles times Kelvin. Okay, so now I'm going to use that to make sure all of my other units match up. But I'm also going to think about what should that unit for density be. All right, atmospheres matches up. We picked that. Now, I don't see liters anywhere yet. That's going to come in with the density here, so we're going to talk more about that in a moment. Moles matches up right here. This is in Kelvin. I've got Celsius here, so of course we're going to need to add our 273, and that's going to get us 343 Kelvin. All right, so let's talk density for a moment. We can see that the liters didn't match up with anything else. Also, the grams over here didn't match up with anything else. So those two units are what we have for density. Now, as a reminder, density is mass divided by volume, so therefore the unit here would be grams per liter. Again, not milliliters like we're used to seeing for liquids, but rather liters. So be very careful there. All right, so now that I have everything kind of ready to go, I am ready to plug in. All right, so with that said here, my molar mass, as we said, was 32. My density is what I'm trying to solve. My R is 0.0821. My temperature, once I converted it, as a reminder, was 343. Over my pressure of 3. All right, so I need to get density by itself, right? Well, it's already in the numerator, so that's a good spot. So all this other stuff I want to bring over. So I'm going to plug in the 32 into my calculator. That is by itself over here. And I want to think about bringing everything else over. Well, if this is divided by 3, then to bring that over, I would multiply by 3. That would leave density times these other two things. Well, if it's multiplied by these other two things, then to bring them over, I would divide them over. So I would divide by the 0.0821, and then I would also divide by the 343. And that gets us an answer of right around 3.41 once I round for 3 significant figures. So density, 3.41. And as a reminder, as we said up above, our unit is going to be in grams per liter. All right. Now again, there's more than one way to solve that algebra. As long as you're solving it and getting a correct answer, you're good. I just wanted to kind of show y'all how I would have solved it, so that way if you're getting really stuck on it, you kind of have some guidance there. And again, this would still be considered the ideal gas law, even though it's not Pivnert directly, it's a variant of Pivnert, and so therefore we would still call it ideal. All right, y'all, there's one last ideal problem here. It says if the density of gas is known to be 1.96 grams per liter at 755 torr and 5 degrees Celsius, what is the molar mass of the gas? So go ahead, pause the video, take a moment, see if you can try it out. Okay, did you pause it? Did you try it out? I sure hope you did. Let's check and see how we did. All right. So, just like always, started by writing down my data here in dark blue. Density 1.96 grams per liter. Pressure 755 torr. Temperature 5 degrees Celsius. Molar mass, I'm looking for a grams per mole value. I can see that this is one set of conditions, so I know I'm using some variant of Pivnert. However, because this involved molar mass and density, I decided to use the molar mass equals dirt over P equation. However, I still needed to pick an R value. I made sure that my R value that I selected matched up with torr, so therefore I used the 62.4 value. I made sure all my units matched up. So torr obviously matches. Kelvin, I had to convert my temperature. So 5 degrees became 278 Kelvin. Moles would have matched up with the molar mass here. The liters matched up with the density, and so therefore from the density and the molar mass, the grams would have canceled out. So then I just plugged everything in. Now this one, the algebra was pretty easy because everything was already all together on one side. All of my numbers, my unknown variable was by itself. And so all I had to do was plug in that math and I got an answer of 45.0. And again, that's 3 significant figures there because all of the original data had 3 sig figs. It was grams per mole because I was trying to solve a molar mass. And my law name would be ideal. All right, I'm going to tell y'all right now the best way to get good at these problems and figuring out how these are different than Boyle-Charles Gay-Lussac's combined. Also figuring out how to pick the correct formula. Do I use the dirt over P one? Do I use the Pivnert one? Practice. You got to practice with these, y'all. The more you practice with it, the more efficient you're going to get. All right? All right, if you have any questions or need any help, please feel free to email me. Bye, guys.